Good morning. We are intelliGrid, and we did SDG&E's Smart Grid Demonstration Model. I'd like to take a minute or two to introduce the team. I'll start with the software team. Keisha Tran at the end. She was a user interface programmer and web designer. Lawrence Meyer did the Power World simulation. He was a parts manager. Emmanuel Dimenteverde. He was a PowerPoint manager, as well as the infographics. And Edmund Baswan, he was the simulation design and reports editor. And then we have Brian Rodriguez, who's animation design, as well as technical illustrator. Harrison Snodgrass, lead programmer and project manager for the software team. Gabriel Duran, embedded design and reports editor. Josh Pritz, embedded systems design and PCB design. Tony Nguyen, he was our, I'm sorry, Tony. He was embedded design and document repository manager. Mehmet Isaac was our AutoCAD design and our PowerPoint manager. Lucas Eberelding was parts manager and communication specialist. And last but not least, Rachel Schramm was our SolidWorks engineer, as well as our as well as our website design. And I'm Derek Flesher. I was project manager in embedded design. Our goal was to build a smart grid demonstration model for SDG&E. The model demonstrates SDG&E's ability to dynamically deliver distributed energy resources and its ability, the smart grid's ability to self-heal under multiple fault conditions. Our model consists of a physical model that's based on a landscape of downtown San Diego, as well as an Android application that controls and displays the various states of the physical model. Up next, I'd like to bring up Lawrence to discuss the grid overview.
Thank you. Hello, everyone. I'm going to discuss the design of our power system upon which we based our model. We decided to use a simple loop distribution system that was easy to understand, but could also demonstrate the essential components of a modern smart grid. Our smart grid incorporates renewable energy sources, distributed generation, and switching devices that not only protect the grid, but give it self-heating capabilities as well. For renewable energy sources, we included a photovoltaic power station and a wind farm. Together, these provide around 33% of the power during peak hours. We also have a battery energy storage system, and this is used for load balancing. Basically, it charges during off-peak hours and provides energy during peak hours, and this increases the overall efficiency of our generation systems. Once all this power is generated, it is transmitted to a substation where the voltage is stepped down to 12 kilovolts for distribution. At this level, we also have distributed generation, and this is in the form of residential solar panels. These solar panels decrease the total demand for power. As for the self-healing aspect of the grid, this is accomplished using switches and ties that are centrally controlled by a SCADA system, which stands for supervisory control and data acquisition. Unlike a traditional grid, a smart grid uses digital components which allow it to monitor the electrical characteristics of the grid at all times. So if a fault were to occur, the grid would isolate it and then would reroute power from another feeder. This minimizes the amount of time that customers are without power and gives SDG&E the ability to quickly locate a fault and repair it if necessary. Next, Brian is going to be discussing the power flow of our system.
Thanks, Lawrence. Hello, everyone. So this is a simulation that we used to create for our project. Our project is basically revolving in this simulation. This is done in Power World. Can you play that, please? Okay. So we can see how power is flowing from SDG&E. I'm just going to go over the devices. So these three devices are generators. This is a wind turbine generator. This is SDG&E's conventional power. And this is solar. So power is flowing in this direction. This is the substation, which is represented by a transformer. This is one transformer, and each of the loads has their own transformer. So SDG&E is providing power at 69 kilovolts. Then this is stepped down to 12 kV, as Lawrence said it, and then it goes down again to 120 volts. This values that you see right here in each of the transmission lines represent the percent at which each of the transmission lines is being loaded at. Yeah, oh, this is a fault, this is the next one up. This is the fault. Right now we have a fault in this transmission line, so we can see how the power is being routed through the tie. Can you go back to the previous slide, please? Yeah, because in this one, there's a fault in this section. Let me just show the previous one.
Previous one?
Yeah, that's
Sorry,
it.
connected to the
Yeah, that's it, that's it.
projector
So,
did it, unhappy.
that's fine. So, you can see how this is normal operation. So, you can see how there's two routes. There's the top one and then the bottom. You can see how the power is flowing into each of the different loads. And then if we create a fault, if there's a fault in this section, now you can go to the other one. You can see how this is the tie. The tie is, during normal operation, it has to be open, so no power is flowing through this section. Now I'll go to the next slide. Now, when we have a fault in this section, now you can see how the power is being rerouted through the tie, so the tie closes real fast. So if there's a fault in this section, these two loads never lose power because the tie closes in a fraction of a second, so the user will never even notice that there was an outage in their areas. And next, we'll have Edmond to talk about some algorithms about.
Okay, so we wanted to find a way to put the Power World simulation into our app. We took the Power World generated values and placed them into an array, and each array value represents a new hour. In one of the 3 residential areas, you'll be able to add and remove solar panels and electric vehicles. To account for these features, we created this algorithm. For Res 3, that's the value of the load at each hour. NumEV is the number of electric vehicles that are enabled on the grid. EV is the power consumed by each vehicle. Solar is the strength of the sun throughout the day. And weather is the multiplier of solar, where 1 represents a sunny environment and 0.2 represents a cloudy one. Next. We'll also be able to handle faults in the simulation. If a transformer has a fault at one of the loads, then power doesn't need to be routed as shown before, and power would flow as it normally should. But if a fault occurs at one of the transmission lines, as seen here, then power would then need to be rerouted through the tie switch at the bottom. And to talk about the user interface, here's Keisha.
So we took all of the information that was just presented and integrated it into an Android application that we have running on an Asus tablet. This is our main user interface, and we modeled it after the Power World simulation. Since the Power World simulation is a little too complicated for average users, we wanted our application to be clean and simple for people to use. On the left side, you can see the 3 residential loads, and on the right side are the 3 commercial loads as seen in the Power World. On the top, you can see the solar panels on the right side and the wind turbines on the left that feed green energy into SCG&E substation, which is located in the middle. We also have switches at each load and also transformers and a tie at bottom. We wanted our application to be user-friendly and as easy to use as possible, so we gave it a cartoonish look so users could get the feeling that they're playing a video game. On the top right, we have our control buttons that allow the users to fast forward, play, or pause our simulation's time. All of the transformers, which are the little green boxes at each load, you could click them and they'll display the load's values. The residential houses on the left side are also clickable on load 2 and 3, and it allows the users to add or remove solar panels or electric cars. The user can also simulate faults, so if they click the hazard icon on the right side, it'll allow the user to choose to place a fault at either one of the letters that are displayed at each load, and they can see the resulting effect on the power grid. It's also self-healing, so after a while, the power flow will go back to normal. We also have infographics, so if you click the graph icon on the right side, you can view that And we also have an info page that will give the user instructions on how to use the application. Our design will let users easily navigate through the application and also at the same time learn and understand SDG&E's power grid. Next up is a manual who will talk about the infographics.
When we started, we said that we wanted to make something beautiful and simple. I think we were able to achieve that with this application. We wanted to create an application that provided rich content while still being simple for each and every user. We made this main page as the central hub where each user can control time, simulate a fault, and of course, watch the power flow on the grid. But some of the data points might be confusing to some users. They might wonder, what do the points actually mean? So we created a graph page. The graph page shows all the data visually to the user. As you can see, the residential lines show dip during the day, while commercial lines rise in demand, which makes sense, right? So we thought that the graph itself was going to be an added bonus for the user so they could better understand the overall app and the power flow on the grid. But enough about usability. I know you guys want to see this app in action, so I'm going to have my friend Harrison here show the magic behind the app.
One of the primary problems with dealing with visualizing a power flow in an application is showing it in a way that's readable to the average user. Most people will not understand what reactive power is or what the difference between real and apparent power is. So in order to visualize that, we show the actual flow of power, and how we do that is we use colored orbs. As you can see here, the orb will start from whatever the power source is. In this case, we have a coal plant on the top. Orbs will flow down and branch off at different locations to show where the power is going. In order to do this, we have set up an OpenGL rendering API in order to display these in a quick and efficient manner. The different colors of orbs represent what the source of power is. For a blue orb, it means it comes from a non-renewable source like a power plant. For a green orb, it means it's renewable. It means it comes from a battery or a wind farm or solar panels. Even these residential neighborhoods can create orbs that go back onto the grid, showing the adaptable nature of the smart grid. In order to show a physical representation of this so that multiple people can see the power at the same time, we have a physical model to do this, and I'm going to hand this to Rachel, who will explain how we implemented the physical hardware for this model.
All right, so on top of having an effective app to show the users or customers how the power grid works, we also have a 3D interactive model. You can see it here at the full model. This model gives the customer the ability to interact with the power grid by causing events and then seeing how the grid will recover to these events. We also wanted to give the model a look and feel of San Diego, as this is for San Diego Gas and Electric. The main features that make this look like San Diego, downtown San Diego, is the modeling of the I-5 freeway, the 163 freeway, and the 94 freeway, as well as several buildings, several landmark San Diego buildings. Here's a list of the buildings that we modeled to give the design a look of San Diego. I'm sure you can recognize a few of them. There are also model buildings that are in the San Diego skyline. You can see that their locations on the model do relate to their actual locations in the San Diego skyline. All right, here is Ike to tell you how we are actually mounting this and laying it, and how it's being transported.
Good morning, everyone. So this is the box that we're using for our model. We built it by using 8020 T-slots extrusions, and the dimensions of the box is 2 by 3 feet and 6 inches tall. Well, the city layout that Rachel just presented is placed on the top of the lid, and we use plexiglass acrylic material to support the weight of the entire model. The reason we choose this material because it's easy to drill holes for LEDs, and it's also strong enough to support the printed models on the top. Well, we mounted PCBs, wires, and microcontrollers on the other side of the top plate. So when we lift the lid, everyone will be able to see all the electronic design we built. We also use 100% renewable OCC material to cover all sides of the box because we are an environment-friendly engineering team. Well, lastly, we want to make sure that the model is protected when it's not being displayed. To achieve this, we designed a cover that would protect our model against any possible damages. Next, Brian will introduce you guys to light animation.
Thank you, Mehmet. So this is our preliminary model. You can see how the power is flowing. We're using basically three different colors. It's blue, red, and green. Blue represents conventional energy, which comes from SG&E. Green represents renewable energy, which comes from the solar panels or the wind turbines. The red blocks that you see over there the red LEDs that you see, they are switches, which are the ones that control whenever there's a fault. They're supposed to open if a fault occurs in any of the transmission lines. And you can see how it's very appealing. The light animation that you see right here, it's actually 1-to-1 scale to the app. So users will be able to see how the power is flowing in the model and also in the application. So it's fun. Next, we have Tony, who's going to talk about the light animation of the buildings itself.
Hi. So beside the light animation to show the power flow on the grid, our model also has the ability to simulate San Diegan's nightlife activity. When people go from work, they will turn the light on, and when they go to sleep, they will turn the light off. And this activity will be simulated by changing the intensity of the light. It will get ramped up or down depending on whether people just get home or when they go to sleep. And to accomplish this, we utilize the BWM peripheral of our microcontroller. The output of the BWM will be the duty cycle, and by increasing or decreasing the duty cycle, we can change the intensity of the light. However, due to a sheer numbers of LEDs inside a building, it will lead to a short current if the microcontroller alone is supplying current. To overcome this challenge, we use a low-side switching method to redirect the role of supplying the current from the microcontroller to a voltage source. And with this method, one transistor can be used to supply the current needs for at least 20 LEDs simultaneously without affecting the intensity of the light. And shown here is a short video of one house model during the night phase animation. As you can see, the lights also get flickers to show that the viewers the feeling of there are actually people living in the house. And next, John's going to talk to you about the embedded system and general purpose PCB.
So to bring to life the Power World simulation and the app, we developed a modular embedded system that takes advantage of a Wi-Fi module to allow the tablet to communicate to the model. The Wi-Fi module talks to a master microcontroller using UART, and then the master microcontroller operates multiple slaves, 8 that are in the model. So each house has its own microcontroller that's operating it. There are the light animation has a microcontroller operating it, and also the renewables portion of the model also has a microcontroller. So all those microcontrollers talk to the master microcontroller using I2C. So whenever we started building this, we all realized all the modules were basically the same thing. So we decided to make a microcontroller breakout board that would allow us all to use the same PCB. That way we wouldn't all struggle building our own PCBs. And then there was an added benefit to this. we're not the first team to build a model for SDG&E, and the previous models had maintainability issues. With a modular design like this, SDG&E will be able to easily repair this in the future and keep the model up and running. To talk more about what's going on with the master microcontroller and the Wi-Fi, here's Lucas.
Thank you, Josh. So now we have a simulation tablet and we have an actual model. Communication is a huge key for them to actually work together. So for this, we used our XB Wi-Fi module, and we chose this because it has a feature called soft AP mode, which means we can directly connect the tablet to the Wi-Fi, and with the proper IP address and port number, we can directly transmit data without having to use any other access points. So now that we actually have data coming to our physical model, we need to know what to do with that. So there's going to be information for light animations, whether or not there's a fault. We need to know what's going on. So the master microcontroller takes all that information, figures out what needs to be done with it, and sends it off to the different slave microcontrollers to do their functions. But our hardware model is not just a static model that you can just watch. It's interactive. So the master microcontroller will also call all of the slave microcontrollers and asks for updates, whether or not, hey, did someone hit a dig fault, or did someone put a solar panel or a electric car at one of the houses? And so that will transmit the data back through the Wi-Fi module to the tablet so that it can be updated again for light animation. And to talk about the different interactive houses, here's Gabe.
So in order to make this model look more realistic, we decided to add residential neighborhoods. Now, a lot of these houses are interactive. So as you can see, users can add solar panels, electric cars, and users can also change the, when solar panels are added to the houses, users can modify the level of generation of the solar panels. So if a user places a hand over the houses, it will simulate cloudy conditions and generation will go down. Cars and the solar panels, once they're added, will change the load. They will either increase or decrease the load. And the way that the model knows if these things are added, there's different switches called holophonic switches that are activated through the south pole of the magnet. And these, however, were not the only interactive things in the model. So talk more, be there.
Currently, San Diego Gas and Electric procures 23.6% of their energy from renewable sources. However, the state of California mandates that by 2020, that'd be 33%. So to do this, they've recently purchased contracts with solar companies and wind companies in Kern and Riverside counties and Imperial County to buy wind and solar energy. So we've incorporated these at the edge of our model. The wind turbines are interactive through the use of a rotary encoder, and they're also the speed is also set by software. The solar panels are interactive through the use of a ultrasonic rangefinder, in which users can place their hand over the model and simulate cloud cover, which will then affect the amount of solar generation coming from the solar panels. With many sources of generation and many hours of off and on hours of energy requirements, sometimes more energy is produced than is required. So SDG&E uses battery storage to load balance when generation is lower than required energy needs. And however, that is not interactive. It's only set by software. It's represented using 3 LEDs. Up next is Lawrence to discuss the budget.
So we had a very generous budget thanks to our sponsors at San Diego Gas and Electric. The major cost came from the hardware side. The most expensive part was actually 3D printing of our models. That cost a little over $1,000. Our next biggest cost was the LEDs that were used in our light animation. The other items, specifically with the hardware, they weren't a lot individually, but together they added up to quite a bit. On the software side, our biggest cost was the Android tablet, and because most of the work was just being done through programming. And I'm going to bring up Derek one more time to wrap things up.
Thank you, Lawrence. In closing, we'd like to thank John and Mark for their mentorship throughout this process. We'd like to thank the SDG&E team, Steve, Daniel, Darren, and Alan, for sponsoring and helping us throughout this process. And we'd like to open it up now for any questions.